Hi, this is Professor Gina, and I'm going to do a second part of examples for section 8.6. These are two application problems. This first problem is a repeat of one that we did in section 8.5, and we used a different method to solve it in the last section. In this example, we're going to use vectors and the components of vectors to solve the same problem. So I'll draw a picture to kind of remind you of how this was started. We'll have, anytime that you have a direction or direction that something is moving, and there's no north, south, east, west given, we start in a northern facing direction and then we move clockwise for the angle. And so in this particular case, if I start north and I'm going 32 degrees, I'm going to open this way 32 degrees. And this is the direction that the plane is moving. And it says it went 210 kilometers. And then it's going to go 280 degrees. So I start again by making sort of a new axis system here. And so that 280 degrees is going to swing around like this. And the plane is going to go this way for a while. Let's see, it was 170 kilometers. Not drawn to scale, but you get the idea. And so if I have this sort of horizontal drawn here, I can see that this angle here is going to be 10 degrees because swinging all the way around was 280, and if I went 3/4 of the way, it would be 270. And what we're trying to find is the direction from the starting point that the plane ends up, and then also the magnitude, or the length, in this case, the length of the vector, how far it is from its starting point. So there's a couple of different ideas that are happening here. If I think of this first vector that's drawn, the one that's gone 210 kilometers, and I draw a triangle to get the two components for it. Because this angle that's over here is 32 degrees, I know that this is going to be 58 degrees. And so what I'm trying to find are the two components here, like in the x direction and in the y direction. So for the first vector, we'll say that it's going to be the length that's given. So it's going to be, clearly I'm tired. (210) times the cosine of 58 degrees. Cosine is going to give us that x component. And then that's going to be multiplied by I. That lets us know that it's in the direction going left, right? And then 210, again, that's the length of the vector, times the sine of 58 degrees times j. That lets us know that we're going in the direction up, down. So those are the component vectors for the first vector. The second vector, I'm going to draw a different triangle. For the second vector, we have sort of this situation happening here, where this was 10 degrees. But we're always coming from a positive x-axis, and so we're actually looking at this angle here, which is 170 degrees. We could use the 10 degrees, but we're then going to have to think about positive, negative, and we're, take that into account. So for our second vector, we take the length, which was 170 kilometers, times the cosine of 170 degrees, and then plus, times I plus 170 times the sine of 170 degrees, J. Just a coincidence that the same numbers there. So the result, when we have two vectors that are added together, talking about the blue, the result is the magenta that's on the side, and you take the two vectors that you had started and you add them together to get the result. So I'm going to take these two components and add them together. So I'm going to have, so the resultant vector will be 210 cosine 58 degrees plus 170 times the cosine of 170 degrees I plus, put it on the second line here, we had 210 times the sine of 58 degrees plus 170 times the sine of 170 degrees, J. And then we'll plug that whole thing into the calculator. And we get negative 56.13 I plus 207.61 J. So looking back at our picture, we're looking at that magenta vector, and those are the components that make up this triangle here. And then the second part was to find the magnitude of, or the distance, right? And so now that we've found these two components, we'll use the numbers in the Pythagorean identity to find the length. So the magnitude, we did this example in section 8.5, we were calling it the distance the plane was from its starting point. We'll have square root of negative 56.13 squared plus 207.61 squared. And putting that into the calculator, you should get 215 miles approximately, which is the same answer that we got when we did the problem the other way. Okay, let me get a new piece of paper here. All right, this problem is taking force into account and looking at an object that is suspended by two ropes, and it weighs 2,500 kilograms. And we want to find the tension in each of the two ropes that are existing. Oh, wait, pause. I got to go back because I forgot to find the direction of the airplane. Just realized looking at my notes. Hold on. Sorry. Let me pause for a second. Sorry, I just paused and came back because I realized that I didn't finish this problem. That we still need to find the direction that the plane is from its starting point. And so I'm going to draw a new version of this because I've got a lot of pictures going on here. We have the plane has ended up over here. And what we're trying to figure out is what this angle is going in this direction. Because remember that when we talk about direction, we're going from a northern face and then going clockwise. So that's where we're trying to, the angle that we're trying to find based on the two component vectors that were put together to start. So we know, because we just found this vector, we found the x component and the y component for this. And so if we were to draw the triangle here, we know that this length here is negative 56.13, and this length here is 207.61. And so we are going to use the tangent, right? We're going to try to find the angle there. So we know that tangent inverse, or tangent of the angle, is going to be the opposite side, 207.61, over the adjacent side, negative 56.13. Or theta is tan inverse 207.61 over negative 56.13, which gives us, because of the inverse function of tangent, we get a negative angle, we get negative 75 degrees. But negative 75 degrees is in the fourth quadrant. So if we add 180 to bring it into the second quadrant, we'll be at 105 degrees, right? So if this is 105 degrees, then what is the green angle? That's 105. That means that this is 75. And notice that the green is not starting from the positive x-axis, but it's starting from the north, right? So I've gone 270 degrees to here, plus another 75. So I think that the angle is going to be 207 degrees plus another 75. So theta is going to be 345. And again, that's the same answer that we got when we did the problem in the last section. Okay, moving back to the other question that we just had. Sorry, I'm skipping around a little bit. We're looking at a block that's suspended by two ropes, and we want to find the tension in each rope. I'm going to draw a picture that will kind of give us a different perspective of what's happening here. So vector S, we'll call this one. And this angle is going to be 30 degrees. We know that because of the way that they have it drawn, they have 60 up here. And then we've got another angle over here. We'll call that vector R. And we know that this angle is going to be 45 degrees because the way they've got it, they've got 45 up here. Right? And then this whole angle here is 135 degrees, right? Okay. And then we'll call this W. This is going to be the weight that's going down. So S and R represent the two ropes. So vector R is going to be whatever the length or the tension of that vector is. And the two components are cosine of 135 degrees times I plus sine times 135 degrees times J. Similarly for S, it's going to be whatever the magnitude of that vector is, or the tension, and then multiplying by the two components, cosine of 30 degrees times I plus the sine of 30 degrees times J. So what I'm doing is I'm taking the two components of the vector, and then I'm multiplying by the magnitude of that vector, which is the part I don't know. The thing in absolute values is the magnitude. And then for vector W, that one we do know the magnitude of. We know that the magnitude of that is 2,500 because that's the weight. That's the weight of it, right? So for vector W, it's going to be 2,500 cosine of, that's 270 degrees, times I, plus sine of 270 degrees times J. So if I kind of put these all together using what I know about the cosine and the sine of these values, I have negative square root 2, actually, yeah, over 2 times R times I plus square root 2 over 2 times R times J. Here we've got square root 3 over 2 times S times I, and then 1/2 S J. Cosine of 270 is 0, so I've only got 2,500 times J. Because the sine of 270 is, oh, that's going to be negative, right? Okay. So when I have a system like this that is in equilibrium, we need to have balance among all the different vectors. So that means that the three vectors that we have, R and S and W, have to total out to be 0, the 0 vector, or 0I plus 0J, the 0 vector. So everything that I have over here is a system of equations, and I need them all to equal to 0. So I'm going to put these together. I'm going to put the I components together, and I'm going to put the J components together. So I've got two different equations, right? The side on the left should total out to 0I, and the total on the right should total out to 0J. So putting these together, I'll have negative root 2 over 2 times R plus root 3 over 2 times S should equal 0. That's taking the left column on its own. The right column is going to be root 2 over 2 times R plus 1/2 S equals, or actually, let's do minus 2,500 equals 0. I'm going to rewrite this again, moving the 2,500 over to the right-hand side. This is called a system of equations that we're going to solve simultaneously. And because I've got two of the components that are the same, I can add these systems together and I can get one of the variables to be eliminated. So all I did is rewrite everything, moving the 2,500 over to the right-hand side. So now what I'm going to do is actually add these two together. In that first column, I've got that negative square root 2, positive square root 2. Those are going to cancel each other. And so then I get square root 3 over 2 plus 1/2 times the length of S is equal to 2,500. And then I can see that the magnitude of S, or in this case, the tension, is going to be this. And I can plug that into the calculator and get that particular rope is holding approximately 1,830 kilograms of the weight. Now I'll take that value back to one of the first equation. Take it back to the first equation up there. So I have, actually, let me see if I can do this. I think I can get crafty here and copy. Ooh, now I'm learning. Will it work? Ah, I thought it would work. Let's see if I use my mouse. There we go. Yay. Okay, so I took that first equation, and what I'm going to do is I'm going to put 1830 in the place of S, because I just found that. So I have negative root 2 over 2 R plus root 3 over 2 times 1830 equals 0. Negative root 2 over 2 times R equals negative root 3 over 2 times 1830. And then R is going to be negative square root of 3 over 2 times 1830 divided by negative root 2 over 2. And then plug that whole thing into your calculator, and you will get that the tension on rope R is 2,241 kilograms. All right, thank you for watching. I need to go to bed because now it is after midnight and it's Mother's Day, and hope that you all have the chance to spend time with your moms, or at least give them a call. Have a great weekend.